Assalamualaikum and a very good morning greeting to both of my panel, Dr. Abdul Qadir and Encik Azwaj, and also not forgotten my supervisor, Dr. Muhammad Sahar. My name is Ahmad Hadri bin Wadnodin, and today I will be representing my final year project 2 about the title Self-Driving Car Using Deep Learning. So, we started about the project background. In recent advancement, artificial intelligence and machine learning had made a significant growth of interest in developing intelligent vehicle. An autonomous vehicle were the most recently having the highest rate in terms of its safety and behavioral performance of the car. A self-driving car must be able to navigate successfully during driving, especially driving at straight road, curved road, or as well as sharp turns. The behavioral accuracy of the self-driving car depends significantly based on the trained neural network model and robust dataset collection. Moving on to our problem statement, there are two problem statements, which is the first problem statement is vehicle crashes remain the leading cause of accident, death and injuries in Malaysia. The second one is most of the vehicle road accident happens because of the human error and human factor, which can be overcome and prevented by an advancement of technology such as autonomous driving. So, human error and human factor can be referred as example of drowsiness, carelessness. So, this kind of factor can be overcome if we have autonomous driving. The figure below here shows the Malaysian road accident number of accident from 2010 to 2011. So 2010 to 2019, it shows an increasing trend. But in terms of road fatalities or casualty of the victim, it shows a decrease value, decreasing in trend. Why decrease? Because we have improved in terms of our technology in the car development or car technology, such as electronic brake distribution, ABS, airbags, and so on. Which means it shows that technology can improve the safety of the passenger. Next is the objective, which is the first one is to apply deep learning algorithm using convolutional neural network. The second one is to implement data augmentation technique for optimization of the neural network. And the third objective is to measure the performance and demonstrate a simulation of a fully functional car that drives autonomously. Scope of the project. The first scope is data augmentation library that you use is named IMGOP, or the full name is Image Argument Library. And then deep learning convolutional neural network is used to develop the network model. The third one is Udacity open source self-driving car simulator is used to perform the final simulation. The fourth one is the program algorithm involved in using Python and libraries such as OpenCV, TensorFlow, and Keras. And the final scope is the track or type road condition that will be used for our simulation testing is type of road, which is a straight road, curved road, and sharp turn. A bit about the literature review. So there are three authors here, which I'll be summarizing. The first author have done about detection of deep learning for autonomous driving application. It uses hybrid local multiple SVM CNN model, but for our purpose, our project, we only utilize the architecture of CNN. The second author project title Evaluating Deep Learning Architecture for Speech Emotion Recognition. It uses a method of CNN and recurrent neural network with long short-term memory, but unfortunately we only utilize the CNN architecture. And the last one is the third author, project title Regularization and Optimization Strategy in Deep CNN. It uses a method to optimize the neural network using data augmentation technique. This one we utilize the processing using the data augmentation. Next is the methodology of the flowchart, where we started our project by input dataset images, followed by 7 relative process: collecting data and balancing data, training the data and validation data, pre-processing data, convolutional neural network, data augmentation for optimization, test and measure the performance, and finally is the output simulation of the car simulation itself. Okay. So each method will be explained as a bit. The first method is the data collection. Here it shows the collected data set of the driving vehicle, which it shows each images contain its relative parameter such as steering angle, throttle, reverse, and speed. Next, the dataset were transformed into an histogram graph, which shows here during our collecting data session. It shows that our car drive mainly in a straight line. So this straight line here will causing a bias towards the dataset for our trained neural network. Therefore, we need to eliminate the straight line, or we can call it as a zero angle, because here from 0 to positive 1 is right steering angle, and 0 to negative 1 is the left steering angle. So here now, after we have modified our uh, dataset histogram, it shows that our dataset of a steering angle were relatively uniform, as it has a uniform distribution of right steering angle turning and left steering angle turn, and as well as a bit bias in zero angle, as because we wanted the car to ensure that it drive mainly at the center of the road. And then the third method is to split our data into training set and validation set. This is important because we will train our neural network using the validation and training set. Next method is pre-processing data. The dataset will be pre-processed, which you can show here. This is the final pre-processed image, which this is the original image, but the pre-processed image have become cropped and apply YUV color space as well as Gaussian filter, because we want to eliminate uh, unnecessary features and noise. And then our next method is the convolutional neural network. Here it shows the input plane, and then normalize, followed by we have three convolutional layer and three dense layer, which is the fully connected layer before the output. Next is the data augmentation. So data augmentation involved in four data augmentation. The first one, we augmented the data set to be optimized in terms of zoom augmented image. Here we can see the original image and the after image that have been augmented or after being optimized. It has been zoomed, so we can see the hood of the car cannot be seen because the image has already enlarged. Then next is the pan argument image. This is the rotation of the horizontal or vertical of the image. And then is the brightness altered augmented image. You can see the original image is a bit brighter, while the brightness of the after augmentation image is a bit darker. And last one is the flip argument image with the relative steering angle. You can see the original image showing the steering angle were at 0.07, were having a right turn. When it flip, it shows a negative to the left, which is to the left turn. Excuse me, sorry. So now we come to the important part, which is the result discussion. Here it shows the convolutional neural network that we have developed, which using the first approach, which is the ReLU. We use the ReLU activation function. So here is the model summary, where it shows the convolutional layer. We have five. Uh, uh, we have two dropout layer between the flattened layer, between each flattened layer and also dense layer, and then three dense layer, which is the fully connected layer. So okay, here come the important analysis. So the CNN development using ReLU activation function have uh, provided or obtained a graph, learn curve graph, which is we call that ReLU. So we can see here the graph. Here is the result of the graph of training loss and validation loss. So it shows unsynchronized pattern, uh, and also it also merged too early. So if the value of feed input into the ReLU uh, was 0 or greater, then the ReLU function simply returns the exact same value. Okay, here it means that why we got the uh, unnecessary result here, because when we use the ReLU function, uh, here from the graph of the ReLU we can see that ReLU have a positive gradient in the positive region and a negative gradient in the negative region. Therefore, uh, when the value of the ReLU is greater, so it will returns the exact same value. But when the nodes get an input of negative number, so it will return a negative 0 value. Therefore, when a negative 0 value input into the neuron uh, input, so it will become the network model will not getting trained and learned, so it will produce an inaccurate result. So now is the second approach, which is the ELU activation function. So this is the model summary. The model summary is exactly the same with the previous ReLU. The difference in terms of its learn curve graph, there's a little bit different, where we implemented ReLU because we wanted to improvise from the previous obtained curve graph. Here it shows that our graph obtained a bit better result, um, where because of LU activation function, which if you can see here, it have a non-zero gradient value in negative region, so indicating that the LU function always have a chance to recover and fix its weight parameter in order to decrease its error. So the network will become continuously trained and processed instead of become dying node like ReLU before. So next is the additional dropout layer. So additional dropout layer here tells us the exact same conventional layer, uh, but the dropout level has increased from 2 to becomes 4. 1, 2, 3, 4. Okay, so the learn curve graph shows that the model successfully converged at the end of the epoch process, showing that the train loss and validation loss fit and learn perfectly to generate a good working of neural network model. So here the graph shows it finally converged between the validation and the training graph. So the analysis of the convolutional neural network after implementation of the optimization. So after we use three approach of using dataset without optimization, now we use the dataset with optimization, that we implement the data augmentation technique. So here it shows that the obtained epoch validation loss of CNN network with dropout layer, it shows minimum here for loss training and minimum here for validation loss. Same goes for evaluation of epoch for CNN. This one without dropout layer, so it shows a better result. It's okay, we will see after this. So the final analysis have provided us that when we use optimized dataset, it produces a very significant difference in terms of the performance of the trained neural model. So here it shows the post optimization of CNN with dropout layer. So actually the graph is already good, but they still have a gap, which is we can narrow it a bit to get much, and it is also under figure if you can see. And then here we can see the best result is the post optimization of CNN without dropout layer. So as we reduce or we eliminate the dropout layer, we can see that the model graph finally the validation uh, converge at the end of the epoch process of this network model. So this is the performance of table comparison result and discussion. So based on 5 approach that we have implemented, 3 of them were not applied augmentation and 2 of them applied optimization. And the best result or the best approach that we've obtained is the 5th approach, the last approach, which is the CNN network model using optimization without dropout layers. So why? Because here we can see it has the lowest validation loss of 0.0317 compared to all other approach. So discussion based on the table comparison. With respect to all 5 approach, the comparison shows that the development of CNN based on data augmentation without dropout layers, or known as approach 5, had become the most successful approach. This is because it had the lowest value of validation loss at 0.0317 at the lowest value training of 0.0324. So the difference value were outstandingly the lowest, which were at 0.007, since the validation loss is inversely proportional to accuracy. Thus it have the highest amount of accuracy since it had the lowest validation loss value. So to conclude, the training of the convolutional neural network were done using several different approaches in order to identify which approach is the best model of the neural network and have the highest accuracy with the lowest value of validation and training loss. Besides that, we also implement the optimization using data augmentation technique, which is shown a proven significant improvement, which is decrease the validation loss and training loss to the it decreased the validation loss and training loss to the lowest recorded value, which make the model very well trained and efficient for predicting the steering angle or to make decision. So recommendation for future is we can implement vehicle detection, and as well as we also can implement pedestrian collision avoidance detection. So now is the simulation result of the self-driving car. So I will play and I will show the simulation. So now as we open the simulator, we select the autonomous mode. Okay, now we can see that the car is already started to drive autonomously. Here it shows the respective steering angle value, and here it shows the relative speed of the car. Here it shows at the result of the command prompt. Here it shows the output of the steering angle that is predicted by the network model. Okay, our car seems to be moving right and left. Okay, now it will encounter a sharp left turn. Yeah, and our model seems to be working really well. Although sometimes it enter the edges of the lane line of the road boundary, but it managed to recover to be at the center of the road, which is the center of the road is the ideal position of the car. So that's all from me. uh, Thank you.